Polynomial rings. This is the 16th chapter from Gallian's abstract algebra. We have in fact actually gone through polynomial rings in Herstein's topics in algebra, but since one of you requested, so we are again going to see. Although there is a slight difference between what we saw in Herstein and what we are going to see here, but essentially this is a repetition. And unfortunately, if we go through this kind of repetitions quite often, then we will be trapped in only one place. We won't be able to progress. Anyway, let's just see what this text says about polynomials. It starts with this definition. And this definition has a name also. Ring of polynomials over R. And the definition goes like this: let R be a commutative ring. The set of formal symbols let's just first write the set and then we will see what this set is, that is what its elements are. N is a non-negative integer. Is called the ring of polynomials in X over R. Now there are some things to be said here itself. What we have done here is just simply this: we have started with a commutative ring R. So in place of R, commutative ring means any ring where the multiplication is commutative. So in place of R, you cannot, for example, choose the ring of R 2 by 2 real matrices, because we know that that ring is not commutative. You can choose, for example, in place of R, the ring of ordinary ring of integers, it's a commutative ring, or the ring of real numbers. Such things you can choose. You can also choose, for example, the ring of integers modulo 3. You can choose finite rings. Okay. Now, the set of formal symbols, these are the formal symbols. Okay, this expression that starts from here and ends here, these we are calling these things formal symbols, is called the ring of polynomials in X over R. In X means this part of the symbol, these things which look like powers of X. Okay, in their place you have X. You can change this X also. You can write some other symbol Y also. Then in place of X you have to write Y. Over R means the coefficients an minus 1 etc., they are coming from the ring R. Coefficients I am saying because we are familiar with these terminologies. In fact, when in elementary school we transitioned from arithmetic to algebra, polynomials are the first thing which we encounter. You see, when we were told about algebra in school, before algebra we did not know anything about variables or something like that. We only knew about numbers, addition, multiplication, subtraction, division, those operations. But when we were introduced to algebra, the first things we saw are symbols like this: x square, 3x cube minus 2, etc. Many such symbols. Now, actually, later on, when things got somewhat more complicated, we encountered such expressions where the coefficients, that is these numbers which appear before those powers of x, these coefficients were allowed to be non-integral rational numbers. But most often in the elementary treatment of these things, the coefficients that we considered were mostly integers. Now comes a very crucial difference between these symbols and these symbols. You see, in school what we were taught is this: an unknown number. For us back then, the only things we had in our mind were numbers. Only objects we knew of were numbers. And we did not, in fact, also have the maturity to ask what type of numbers. For us, numbers meant numbers. So that means x is some number which we do not know. Algebra taught us to add to such expressions without knowing x. Okay. For us, in the back of our mind, whether we were thinking consciously or subconsciously, these minus 2x, x square were ultimately numbers, unknown numbers. Once one knows x, one knows what minus 2x is. So there was no problem in adding these things because they are just some unknown numbers, we are adding numbers. Here, however, that's not how these symbols are to be interpreted. Now x is not a number. You can say, of course, x is not a number because we are no longer in the realm of real number system or something like that. We have a general commutative ring. You may be clever and try to think that similarly x is an unknown ring element, so that this is an unknown ring element. Once one knows what x is from this ring R, one knows this ring element. No, this is not a ring element. Okay, this is something else. That's why we say formal symbols. These symbols have the forms of these symbols, but there is a difference. Here x was an unknown number or an unknown quantity. Here x is nothing. Nothing means these powers of x only tell us where the coefficients are appearing in this total symbol. By themselves, these powers have no meaning. Okay, and in particular, x itself does not have any meaning. And in particular, x is not an unknown ring element. Okay, x is just an abstract symbol whose sole purpose is to keep track of these coefficients, ai's. Fine. Now there are some more things. Note that in this set you can change two kinds of things. One is this n is a non-negative integer. So although x does not have any any meaning by itself, but the exponents of x, you can call them exponents if you want, because that's how they look. These n minus 1, these are integers, and in fact n itself is a non-negative integer. You can change n. The smallest possible value of n that can be taken is 0. You can take n equal to 0, or you can take a very large value of n, some very big positive integer. So you can take n equal to 100 also. That is one thing. Another thing is, after choosing n, you can choose these coefficients to be any ring elements. Okay, that's how you get for all the formal symbols in this set. To represent the fact that the symbol x that we have here is actually x, we write x here, and to represent the fact that the coefficients are coming from R, we write R here. Okay. Now you may notice that we are saying that this set is called the ring of polynomials in X over R. Over R, of course, means the coefficients are coming from R, but for the set to be a ring, there should be an addition, a multiplication, so that those ring axioms should be true. Those things are coming. Okay, this definition should not be thought of as it has stopped here itself. No, we are going to define addition, multiplication in the familiar way. But before we do anything, we need to decide when two such symbols are equal and when two such symbols are not equal. That is, we need to define the relation of equality on this set, and that comes next. Two elements okay, instead of just simply writing in X over R, the author has written, in fact that's how it should be written, in the indeterminate X over R. X is an indeterminate, not an unknown. Okay, X is not supposed to be determined. Okay, it does not make sense to say that we are going to determine X. Two elements anx to the power n plus this plus a1x plus a0 and bm for two such elements of Rx, they are considered equal if and only if we sometimes vaguely say that the corresponding coefficients are equal. Precisely that means this, if and only if AI is equal to BI for all non-negative integers I. Okay, there may be a slight confusion if we just leave it like this. The confusion arises because of this fact. If your first formal symbol is this, and your second formal symbol is say this, then according to this this convention or this definition of equality, these two will be equal if and only if AI is equal to BI. So that means B0 should be equal to A0, B1 should be equal to A1, B2 should be equal to A2. But where is B3? We don't see any B3 here. So for such purposes, B3 and any other coefficient belonging to some higher powers of x are considered to be 0. We consider that there is B3, but that B3 is actually 0, and this is actually 0. Okay, that's how we make the two polynomials you can say have the same number of terms by introducing extra terms if necessary. So under this convention, now it makes sense to say that AI should be equal to BI for all non-negative integers I. If you want, you can think of other invisible terms here also, but they won't serve any purpose here, because you can go like this. You can consider A4, A5, A6, etc., which are all 0. Here also you can consider B4, B5, B6, etc., which are also 0. The thing is that you make the two polynomials have the same number of terms by introducing necessary invisible terms. Okay, not unnecessary invisible terms. Then you can introduce unnecessary terms as many as you want, but they will not change anything. So along with this, we have to add this extra part so that this makes sense. Define AI to be equal to 0 when I is greater than n, and BI to be equal to 0 if I is greater than m. We had to define this because keep in mind that since these expressions for us are no longer elements in R, okay, because we cannot think of x as an unknown element in the ring, so these are not unknown elements in R. Had that been the case, you could have just simply, without defining anything, introduced an invisible term, but that way now we cannot do, because these are formal symbols. And one more thing I forgot to say, because these are formal symbols and they are not to be treated as some expression in R, these pluses are not ordinary addition or addition in R. Okay, these pluses are also part of this formal symbol, and they are not to be treated as some operation. Their sole purpose is to bind these parts into one object. Okay, it's like a glue. you use the glue to bind these things together to make one symbol. Yeah, and these things now the author is going to say these things here. In this definition, the symbols x, x square, etc., x to the power n do not represent unknown elements. Yes. Unknown elements or variables. From the ring R. Rather, their purpose is to serve as convenient placeholders. That separate the ring elements. The coefficients are of course ring elements, but it separates them, and I would in fact add more, not just separate them but tell them what their what each of them has. I mean, what I'm trying to say, I could not in fact frame the sentence itself. What the hell? These powers tell these elements where they should appear in the formal symbol. Okay, it tells them their places. We could have avoided this way of representing polynomials by defining polynomials as some infinite sequences. this infinite sequence. Thus, such a sequence also separates these ring elements and tells them what their places are. So that can also be done, and in fact in some treatments that's how a polynomial is defined. Okay, but our method takes advantage of the fact that we are already familiar with polynomial expressions from our school days. So that way of introducing polynomials is more natural to us, not the sequence way. Okay, what is he saying? Our method takes advantage of the student's experience in manipulating polynomials where x is actually considered as a variable. There is a disadvantage, however, and that disadvantage is just that because we are so familiar with polynomial expressions where x is actually a variable from our school days that we may not be able to distinguish between those expressions and the formal symbols that we have now. In the author's words, the disadvantage of our method is that one must be careful. Of our method is that one must be careful to not confuse a polynomial with the function determined by that polynomial. What this means is that if without being too abstract, we take one real polynomial, say 2x square plus 3. when we are considering this as an element in this polynomial ring, then it's just a formal symbol where these 2 and 3 are real numbers, and that's all. And of course there is this 2 here also. Okay. However, when you consider the function determined by this polynomial, then you are talking about this real valued function whose rule or formula is this, and f is a function mapping the set of real numbers into the set of real numbers. These two things are entirely different. Here x is actually an unknown. In fact, it's a real variable. You can put real numbers in place of x, and you can evaluate this function at those real numbers. The polynomial expression is an abstract object. It's just a formal symbol where x has no meaning. As yet, x has no separate meaning. This confusion does not arise if one takes the sequence approach in defining polynomials, because then instead of considering this expression, our polynomial will be just this 3 0 2 0 0 etc. This infinite sequence. You may say that these two things are entirely different. Well, they are, strictly speaking, they are different, but you will see that if one defines polynomials like this using some relevant addition and multiplication, if one defines a ring structure on this, and if one defines a ring structure using these expressions, then the correspondence between this type of expressions and the corresponding sequences, there is a correspondence, a function, no? So that function becomes a ring isomorphism. These two rings, essentially ring theoretically, they become the same thing. So one can either use this or this technique of defining polynomials. We are using this because we are more familiar with this. That is the advantage. But the disadvantage is that while doing this, we should not think that these are functions. That is, we should not think that x is an unknown ring element. And to see what can happen if one forgets this distinction, the author has provided one example. For example, in the ring C3x, the polynomials fx equal to x and gx equal to x cube determine the same function. This the lack of distinction is made worse further by using this kind of symbols to denote polynomials. They look exactly like functions, but now they are not functions actually. That f of x just simply is a name given to this polynomial x. It is some polynomial in x. Okay, it's not a function of x. In that sense, we are using f of x. And these two polynomials, you see, according to the definition of equality of polynomials, these two polynomials are not the same. Why? Because you can write fx like this. X plus, or okay, the way we are writing these symbols, 0x cube plus 0x square plus x means actually 1x, whereas g of x is 1x cube plus 0x square plus 0x. Here we have different coefficients. Here also we have different coefficients. So as polynomials, these two are not equal. They are not the same polynomial. However, they determine the same function. If you use these polynomials to define functions, the first function, if we decide to call it also f, somewhat confusingly, if we treat x as an unknown ring element, now our ring is Z3, okay, keep that in mind, then these are two functions. These functions are the same because in Z3 x is equal to x cube. Which you can verify easily because there are only three elements in Z3, 0, 1 and 2. You just substitute those values here, you will see that this equation is true in Z. In fact, this equation is an identity in Z3. It's always true for any x. So now we are going to write those things. Determine the same function from C3 to Z3, since the reason is simply this: f of a is equal to g of a for all a belonging to Z3. This, however, we should say what f of a means, because we are going on saying that we should not think of x as a variable, but it seems like we are treating x as a variable. But here this f of a and g of a are those functions being evaluated at a, which f of x and g of x, these polynomials determine respectively. Okay. Anyway, the author writes as a footnote, actually, in general, given any polynomial fx in Rx, here fx is a polynomial, okay. When we say in Rx, that means this is the polynomial, not a polynomial function. And a in R, f of a means substitute a for x, in the formula for f of x. This substitution is a homomorphism of the ring Rx to the ring R. Okay, that is if one associates the polynomial f of x and the ring element f of a, where one keeps a constant, okay, then one gets a ring homomorphism from Rx to R. But fx and gx are different elements in C3 x. Okay, that's the point. And there is one more point which is very nice that the author has mentioned here. One observation. Also, but let us just pour some ink down. Also, in the ring, Cnx, if you want to roughly know what is going on in mathematics or physics or computer science, what research is going on, you can look here. You will find many nice articles in Quantum magazine. Okay, just it crossed my mind, so thought of telling you. Quantum magazine. To exactly know what is going on in some particular topic in say mathematics, you of course have to look at relevant research journals. You have to go through the papers. Okay, so what we are saying here, additionally, also in the ring Z and X, be careful to reduce only the coefficients. And not exponents, only the coefficients and not the exponents modulo a, modulo n. What this means is this. in Z3x, 5x is equal to 2x, but these are not equal. Okay, so in the frenzy of reducing everything modulo n, you will of course reduce the coefficients. 5 actually means 2 in Z3, but that won't work with the exponents. X to the power 5 and x square are not equal, so don't reduce 5 to 2 modulo 3 here in the exponent. That's what the author is saying. Okay, now we come to the question of the addition and multiplication in this ring. To make Rx into a ring, we define addition and multiplication in this set in the usual way, which however is presented as a definition here. And the definition is the one with which we are already familiar. Addition and multiplication in Rx. Oh, I forgot to say something. Remember, in the beginning I said that there is a slight difference between polynomial rings that we are seeing here and the polynomial rings, this type of polynomial rings that we saw in Herstein. The difference is just this. In Herstein, we considered Rx where R is a commutative ring with unit element. Here, however, we are considering only commutative rings. This is not needed. I think the reason Herstein chose to consider those type of rings is that this type of rings often occur in commutative algebra, which gives you the tools to study the algebraic tools to study algebraic geometry. And one is often interested in, this is actually the main point of focus in Herstein's topics in algebra. A polynomial ring over a field, and a field is a commutative ring where there is a unit element, in fact where division is also possible. Here, however, only commutative rings are being considered. Okay, so that is the slight difference. Okay, without further ado, let's just see the definition. Let R be a commutative ring, and let, so we are going to consider two polynomials. Be two polynomials in Rx or belong to Rx. then we are first going to define addition. Polynomials are very important in mathematics in general, not just in algebra. In analysis also polynomials are important. To see why they are important, you probably you already know something about Weierstrass approximation theorem, where a continuous function can be approximated by a polynomial function. Okay, so then addition. F of x plus g of x is just this. As plus bs. Loosely speaking, addition is defined by adding the corresponding coefficients. Plus bs minus 1 times x to the power s, like that. a1 plus b1 times x plus a0 plus b0, where s is the maximum of m and n, and where of course that thing ai is equal to 0 if I is greater than n and pi is equal to 0 if I is greater than m. Okay, so this is used to make both the polynomials have the same number of terms. So we say s is the maximum of m and n because of this. Say you have a3x cube plus a2x square plus a1x plus a0, and you add that with say b1x plus b0. What you then do, first you introduce necessary invisible terms. So we don't have to do anything to the first polynomial, because here this 3 is greater than what we have here, 1. So after the introduction of necessary 0 invisible terms, these are not mathematical terminologies, okay? There is nothing, I mean so far I know we don't have anything called invisible terms or something like that. Plus b1x plus b0. So you treat this as b3 and this as b2, and then you perform the addition. That's why the maximum among these two appear there, and that maximum we are denoting by s. So this is addition. Also, the product of fx and gx is this Cn plus m x to the power n plus m plus Cn plus m minus 1 C naught, where Ck is they start. It does not matter where we start, but still maintaining the thing that is written in the text. Ak b naught plus Ak minus 1 b1. So the product of the two polynomials is again a polynomial which looks like this, where the Ck is a sum of such products, where in each product you see this subscripts k0, k minus 1, 1. Sum of those subscripts should be k. All such possible subscripts have to be taken. So eventually here the suffix of a is decreasing and correspondingly the suffix of b is increasing. So eventually we will reach a1, but then here we should have bk minus 1 and then finally a naught bk. For k varying from 0 to n plus m, and here also just like the case of addition, you have to make these adjustments if necessary. Okay, because for example for some particular k, ak may actually be there in the first polynomial, whereas bk may not be there. Okay, if bk is not there, that means bk can be taken as 0. That's what this provision is. This entire thing looks extremely technical and complicated, but you already know that instead of me blabbering, let the author speak. Although the definition of multiplication might appear complicated. Yes, at first glance it might appear complicated, especially to someone who is seeing this for the first time in this general form. It is just a formalization. Of something that we already know. That is, you already know how to multiply two polynomials. What you do to multiply two polynomials, you use the distributive law. That is, if a, b and c are three polynomials, then to calculate a times b plus c, you write ab plus ac. So you use the distributive law, then you collect like terms and combine their coefficients, that gives you the product. So that's what he is saying. It is just a formalization of the familiar process. Of the familiar process of using the distributive law and then collecting like terms. So just multiply two polynomials over a commutative ring in the same way. The way they are usually multiplied. And here is one example. To make the example non-trivial, polynomials will of course be like polynomials, but the coefficients they are going to take from the ring Z3. So that is the unfamiliar part. So we are going to consider two polynomials fx. One of them is 2x cube plus x square plus 2x plus 2, and g of x is 2x square plus 2x plus 1 in C3x. Then according to our notations here, in our preceding notation, okay, see, we are now going to calculate both the sum and the product. However, from the definition we see that the highest exponent that will appear in the product is n plus m, 3 plus 2 is 5. So we will need terms a5 and b5. So let's just accordingly write what those coefficients are. Let's start with 0. A0 is 2, A1 is 2, A2 is 1, A3 is 2, we need A4 also, A4 is 0 and A5 is 0, and B0 is 1, b1 is 2, b2 is 2, b3 is 0, b4 is 0, and b5 is 0. Okay. Then f of x plus g of x, we can write here. Then to calculate f of x plus g of x, you have to see the larger among this n and m. So here it is 3. So that means we will have this. So you can now just simply use the values. A3 is 2, B3 is 0. In fact, let's just write all the things in detail for once at least. Plus A2 plus B2. A2 is 1, B2 is 2. Plus A1 plus B1. A1 is 2, B1 is also 2. And finally, A0 is 2, B0 is 1. Keeping in mind that these are not ordinaries 0, 1 and 2, these are not integers but integers modulo 3, and the sum that we see here is also addition modulo 3. So 2 plus 0 of course is 2, but 1 plus 2 is 3, and modulo 3 is equal to 0. In the ring Z3, 3 and 0 are the same thing. 2 plus 2 is 4, but reduce that modulo 3, you get 1, and this again is 0. So we get 2x cubed plus x, that is the sum. And okay, now we come to the complicated one. Fx gx, but we will just like this one, we will go mechanically. A5 B0 plus A4 B1 plus A3 B2 plus A2 B3 plus A1 B4 plus A0 B5 x to the power 5 plus A4 B0 plus A3 B1 plus A2 B2 plus A1 B3 plus A0 B4 x to the power 4 plus A3 B0 plus A2 B1 plus A1 B2 plus A0 B3 x cube plus A2 B0 plus A1 B1 plus a naught b2 x square plus a1 b naught plus a naught b1 x plus finally a naught b naught. Okay, you can see that the sum of the suffixes subscripts in this first sum, for example, is 5, in the second sum that is 4, and so on. Okay, so let us now carefully write the values. a5 is 0, b5 is also 0. Oh sorry, b naught. See how easily we can make mistakes. a5 is 0, b naught is 1. Okay, then a4 is 0, b1 is 2. Then a3 is 2, b2 is 2, a2 is 1. Then b3 is 0. a1 is 2, b4 is 0. Then a naught b5, a naught is 2, b5 is 0. So times x to the power 5 plus a4 b naught, a4 is 0, b naught is 1. In fact, if we have any ai or bj 0, there is no need to write the other term because it will vanish anyway. Okay, then a4 b naught, a3 b1, a3 is 2, b1 is also 2. a3 b1. Then a2 b2, a2 is 1, b2 is 2 plus a1 b3, a1 is 2, b3 is 0 plus a naught b4, 2 times 0, x to the power 4. Then x cube, a3 b naught, a3 is 2, b naught is 1, a2 b1, a2 is 1, b1 is 2. I hope I have not made any mistake. Plus a1 b2, a1 is 2, b2 is what? 2. Then a naught b3, a naught is 2, b3 is 0 plus then x square, a2 b naught, a2 is 1, b naught is also 1, a2 is 1, b naught is 1. Okay, a1 b1, a1 is 2, b1 is also 2 plus a naught b2. A naught is 2, b2 is 2, x square plus a1 b naught plus a naught b1, a1 b naught plus a naught b1 plus a naught b naught, 2 times 1. Okay, now these two are 0, these two are also 0. 2 times 2 is 4, modulo 3 is 4 is 1. Okay, then this one 4 plus 2 6 and the others are 0. Modulo 3 6 is 0. 2 plus 2 4, 4 plus 4 8, 4 plus 4 8. So modulo 3 this is 2. Then 1 plus 4 plus 4 9, modulo 3 that is 0, plus 2 plus 4 is 6, again this is 0, plus 2. So that means this is x to the power 5 plus 2x cube plus 2. That was a long one. What is the, did I get the correct value? X to, yes. Oh, that means I did not make a mistake. Now of course looking at these things will almost surely repel you so much that you will leave ring theory, but this demonstration has been it is here only for the purpose of showing you that whatever definition we have there, that formal definition is actually what you normally would do to multiply these two things. You won't identify a naught, b naught and all these things, and you won't use the formula mechanically like this. Instead what you will do, you will just multiply these polynomials the way you always do. For example, we were saying there that you use distributive law. Yes, because first you multiply each term here by 2x cube. So 2x cube times 2x square plus 2x cube times 2x, and then when you multiply 2x cube and 2x square, you multiply the coefficients 4 and you, as if you are also multiplying x cube and x square using the rules of exponent, one of the rules of exponent, you write x to the power 5, x to the power 3 plus 2, and then you collect like terms. This of course in this multiplication there is only one x to the power 5, but there may be multiple lower powers of x. For example, if you are looking at x square, x square times 1 is x square, 2x times 2x is 4x square. You would then add those things. So that's what we mean by collecting like terms. Okay, so our general definition and the one we are familiar with are actually the same thing. It is now time to introduce some terminology. For polynomials. With most of what we are going to write now, you are familiar, at least for polynomials with real coefficients. So everything is familiar, only we are now defining them in this much more general setting. If f of x is this polynomial, where an is not equal to 0, the coefficient of the highest term, we can say, because there n is the largest exponent. Okay, in that sense, an is the coefficient of the highest power of x, and if that coefficient is non-zero, we say that f of x has degree n. So that means this polynomial has degree 5, because 5 is the largest exponent, such that in the corresponding term the coefficient 1 is non-zero. Okay, so that is the degree of the polynomial. The term an is called the leading coefficient. It leads all the coefficients, it comes first, and that is why the author is careful to write the highest term first. Okay, he is not carelessly writing a naught plus a1x like that. And if this leading coefficient this or the is equal to the unity of the ring R. Recall that we have defined polynomial ring Rx, where R is any commutative ring. It need not have a unity, but if it has a unity, if it does have a unity, and this leading coefficient turns out to be that unity, for example here the leading coefficient is 1, the unity of the ring, then f of x is called a monic polynomial. That means this is a monic polynomial in C3x. This is not a monic polynomial. Here the leading coefficient 2 is not equal to the unit element. For example, you can think of it as a polynomial over the field of real numbers. This is not a monic polynomial. It is not a monic polynomial and its degree is 1. what else is there? Okay, the zero polynomial where all the coefficients are zero has no degree. For the zero polynomial, we don't define any degree. Fx equal to 0 in Rx has no degree. Remember that no degree does not mean 0 degree. Okay, no degree means no degree at all. There is no notion of degree for the zero polynomial. Polynomials of the form Fx equal to a naught are called constant or constant polynomials. That means a naught is of course a ring element. That means constant polynomials are precisely those polynomials which have degree 0. Either it has degree 0 or it is the zero polynomial. For the zero polynomial there is no degree, but if this constant is non-zero, then that polynomial has degree 0. We often write deg f of x equal to n to indicate that f of x has degree n. And note that according to how we have defined degree and actually according to what degree is, the degree of a polynomial is always a non-negative integer. It cannot be negative. I mean, so far we have seen it is not negative. It can be 0 precisely when the polynomial is a non-zero ring element, or in our terminology when the polynomial is constant, a non-zero constant. As with polynomials with real coefficients, here also we may insert or delete terms of the form 0x to the power k. So this is the same thing as we were saying back then about introducing invisible terms. That same thing the author is saying in this way. We can either insert any such term or not consider, delete any such term. For example, here we have chosen to ignore these things and we have written the polynomial like this. Even before this convention we are using this. Okay, ideally we should not write like this, but this is a following this convention we can write this polynomial much more easily and in a more compact form like this without writing these things. It's understood that whatever terms we don't see here have 0 coefficients. However, keep one thing in mind, that don't interpret this as like this: 2x cube plus 0x square has become 2x cube. No, this plus is not your ring addition. This plus is that symbol plus in the formal symbol. So these terms are there, but they have not been written. 1 times x to the power k is the same as x to the power k. Ideally we should write the 1 here, but if we follow this convention, instead of writing 1 here, we can choose to not write 1. It means that there is 1. And plus minus a won't have space here. Plus minus ak times x to the power k is the same as minus ak x to the power k. We have already used these conventions in those calculations. Okay, now next we look at the first theorem of this chapter. Many properties of the ring R carry over to the polynomial ring Rx. The very first one that we are going to see here is that if R is an integral domain, then so is Rx. The nature of being an integral domain gets carried over to the polynomial ring. So that is our theorem 16(1). And as with everything else in this text, the theorem has a name. D an integral domain implies dx an integral domain. But then again there is the statement of the theorem, which is also the same thing. So this is the name of the theorem, and now we are going to write the statement. It looks hilarious here and somewhat stupid, but in the book it looks nice. If D is an integral domain, then dx is also an integral domain. Proof. Okay. Since dx is a ring. Oh, I think I forgot to mention some things now. After performing that calculation where we found the sum fx plus gx and the product fx gx, there is one small paragraph where the author says, our definitions for addition and multiplication of polynomials were formulated so that these operations are commutative and associative, and also so that multiplication is distributive over addition. We leave the verification that Rx, the polynomial ring, is actually a ring to the reader. This is something very easy to see, that any such polynomial ring is actually a ring under those two operations. It is easy to understand conceptually that it's a ring, but if you really want to formally write down a solution where your exercise is to show that Rx is a ring, it will require some technical writing. Okay, you will have to devise ways of showing that, for example, multiplication is actually associative. You have seen the general definition of multiplication. That itself is somewhat complicated. Conceptually it's not complicated, but representationally it is complicated. It's difficult to represent it generally. But if you want to prove that multiplication is actually associative, you will have to deal with the general case. If you want, I will show you one such solution. Or if you can just take it as a fact that Rx is a ring. So dx is a ring because D is an integral domain. So being an integral domain, D is a commutative ring. So this is a ring. Since D has a unity once the polynomial the constant polynomial fx equal to 1 in dx is a unity in dx, because if one multiplies this constant polynomial with any polynomial, one gets back that any polynomial. Okay, so it acts as a unity in dx. So the what is left for us to show that dx does not have zero divisors. So that means if you choose two non-zero elements in dx, you have to show that their product is non-zero. Now elements in dx are going to be polynomials over d. So let us choose two such polynomials. Next, let fx equal to gx equal to pmx to the power m plus pm minus 1 x to the power m minus 1 etc. plus b1x plus b0 be two elements in Tx such that they are non-zero. And in fact, we assume that these leading coefficients an and bm are non-zero. Had any one of them been zero, there was no point in writing them here. If an, for example, was zero, we would not write this term. We would write some other term which appears after this. And that non-zero term, the first non-zero term, will be the leading coefficient. Assume an to be non-zero and bm to also be non-zero. By the definition of multiplication, the leading coefficient of the product is nothing but their product, the product of these leading coefficients, where an bm is not equal to 0. Where are we getting this from? We are getting this from the fact that this an and bm, like other coefficients, are coming from the integral domain D and they are non-zero. So their product in D is non-zero, is a non-zero integral domain element. Hence, this product is non-zero. So that means dx has no zero divisor. This implies this is an integral domain, and the proof is over. After this, we have division algorithm in a polynomial ring and its consequences, which we will see in the next Gallian video. And you may have noticed that I have not done any group theory exercise today in this video. We will do in the next Gallian video. Half of the video will be on group theory exercises and half will be on rings. And 15, 16, 17. On 17, we will have calculus. So I am going to end the video now. If you want to say something, you can either mail me or you can write in the comment section below. So that will be all for today. See you in the next calculus video, and our usual Gregory Lee's algebra and analysis videos will be uploaded on Saturday and Sunday respectively. So that's just it. See you in the next calculus video. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.